During the time period between 1665 and 1672, Isaac Newton was conducting research and teaching about optics. The former royal scientist of optics was Hooke, to whom Newton disagrees with, both in the realm of physics and in a more personal way as well. Newton believed that light had to be corpuscular, and that color was based on the size of the particle, red light being of a greater mass size and speed, blue light being of a smaller mass size and a slower particle. Hooke believed that light was a spring-like pulse, and that color was based on the compression of the spring-like waves, having red light and blue light be a confused white light pulse, red being more compressed at the first and less compressed near the back, blue light less compressed wave, followed by its more compressed part. This battle between Hooke's ideas and Newton's ideas would persist for hundreds of years. Newton argued that in order for light to travel in straight lines, such as when he made a pinhole light to enter his lab through a window curtain, and for light to reflect off of surfaces, light had to be made of particles. He rejected a dense fluid ether, and that light was a wave of the dense fluid medium itself, stating, quote, "A dense fluid can be of no use for explaining the phenomena of nature. The motions of the planets and comets being better explained without it. It serves only to disturb and retard the motions of those great bodies, and make the frame of nature languish. And therefore to make way for the regular and lasting motions of the planets and comets, it's necessary to empty the heavens of all matter, except perhaps some very thin vapors, steams, or effluvia, arising from the atmospheres of the earth, planets, and comets, and from such an exceedingly rare ethereal medium as we described above." Newton also believed that if, according to Hooke, light consisted only in impressions propagated without actual motion, then in order for the sun to propagate light in every direction in an instant or in time, the light would have to bend into shadows as compressions in a fluid cannot propagate in right lines, and will bend and spread behind an obstacle, meaning the far side of Earth would see daylight bend around the planet, and it would light the sky at night. Newton also wrote that the vortex ether of Descartes and others doesn't account for the moons, as many moons around planets orbit against the supposed flow of the ether. Newton had no answer as to what the ether might be, and the only solution he provides in his book Optics is that God is capable of doing things we don't understand. However, what we got from Newton was that light can be described as a particle that is traveling through a medium. Newton's particles of light were based on the size of particles, and so despite his research on light reflection being quite solid, and being the basis of optics, the corpusculars didn't have as solid of a basis for color and refraction as he had thought. Newton's hypothesis of light was not at all able to explain diffraction or polarization, and for this reason, some of the scientific community preferred Huygens' wave theory of light. Newton had attempted to explain a possible ether theory, but would later abandon it, stating that he did not feel a need to speculate on ether, as his math of the laws of gravity worked just fine without needing to explain the ether. Newton's universe thus sat nearly empty, but being somehow densely packed, but rare enough to not retard the planetary motion. Hence why he abandoned explaining what it could be. Others rejected Newton's universe, as it suggested that things like gravity acted over vast distances without a direct causal link. Gravity is the word Newton coined from the Latin gravitas, meaning weight. This action at a distance problem would prevent a lot of scientists from accepting Newton's theory, as it was considered to be connected with Newton's attempts to bring occult agencies into physics, something Newton was known for. From the Greeks through to the classic natural philosophers like Descartes and Hooke, the ether was the most densely packed thing in the universe, and action at a distance was explained by causal physical collisions throughout the ether. So others saw Newton's action at a distance as impossible, as it would imply that a particle of light is traveling through literal nothingness, which would have only made sense to someone like Heraclitus. One of the scientists that did not believe Newton was the natural philosopher Christian Huygens, who, in 1690, published his book, Treatise on Light. Huygens adopted a more Hooke-like hypothesis of the nature of the universe and light. Huygens assumed that light was just like sound, and that if the ether could be removed, light would vanish too. Huygens held that light was an effect caused by the disturbance of the ether, not a particle traveling through an ether or through nothingness itself. Huygens believed that light, like sound, spread out in spheres, and each ray of the sphere interacts with the medium particle which exists at every point in space, and this elastic billiard ball bumping spawns new spheres of elastic billiard ball bumping at those points in space, called wavelets. Light then is the effect of the elastic collisions of the ether. Another quick recap. Descartes said that space is filled with matter, which is vortexing around stars. He also stated in his theories on the nature of light that it was instantaneous, as is like being poked by a stick. Ether moves, light doesn't. Boyle said that the ether is filled with a subtle matter that explains both the lack of a vacuum and mechanical interactions like magnetism, and possibly other forces like gravity. Ether is stationary, light travels through the ether. Hooke, Boyle's student and assistant, said that the mechanical ether interaction may be like longitudinal spring-like waves, having gravity and other phenomena like light emitting in all directions from the source through the ether. Ether doesn't move, light is like a spring pulse. Newton originally believed that the ether was stationary, and that the density of it got denser near a planet and rarer the further from the planet. But he changed his mind when he considered that the ether would still slow the motions of the planets, and that it may be possible that the ether is immaterial, a decision he left for his readers to decide. Ether unknown or doesn't exist. Light moves as a particle. Huygens had a different form of vortex theory, similar to Descartes in the sense that the vortex threw lighter matter to the edge, and gravity is the effect of the heavier matter being squeezed by the vortex. Huygens' change to the vortex theory was that light was the effect of a wave propagating through the ether. The Cartesian and Huygens theory can be said to be a vortex theory. Boyle and Hooke have a stationary ether, and Newton, though stating that not having an ether is absurd, his math didn't need one and spawned a purely mechanical motion of planets. Every form of wave theory or corpuscular debunking of wave theory was assumed that the waves were longitudinal waves like that of sound. In 1725, James Bradley conducted an experiment that was attempted by two other scientists on different occasions. The experiment was to measure the parallax of a fixed star in order to prove the Copernican model. The first attempt was done by Hooke, but Hooke's telescope did not have enough power to properly observe parallax. Hooke, however, left instructions in the failed experiment's paper, which could be followed to construct a telescope of sufficient power. The second attempt was conducted by Bradley's friend Samuel Molyneux, with Bradley helping him. However, Molyneux unfortunately died, and so in honor of his dear friend, Bradley made the third attempt at the experiment. All three men chose the same star, Gamma Draconis, the head of the Dragon constellation. The star was chosen for the reason that it never sets in England, the country of its measurement, and it passes directly overhead at some point of the day or night. Molyneux's telescope was built to Hooke's description, but Bradley had to have a smaller one constructed after Molyneux died in order to fit it into his observatory. The experiment was to detect stellar parallax, which is an apparent change in the position of a star due to the relative position of the Earth as it orbits the Sun. Bradley expected to find he would have to move his telescope in a circle as Earth circled the Sun, as that motion would make it look like the star is moving in a small circle. What Bradley found, however, was that he would have to move the telescope only half of the year. For one part of the year, the telescope had to be pointing slightly in one direction, hitting a maximum of 20 arcseconds. Then it would return back to 0 arcseconds 4 months later. Then, 4 months later again, he needed to move the telescope to a maximum of 20 arcseconds in the opposite direction. And again, 4 months later, it returned back to 0. And then 4 more, and back to the 20 arcseconds in the first direction. This observations of Bradley's was given a new term, called stellar aberration. And Bradley explained it with a simple analogy. If rain is falling straight down, a man standing still in the rain would see it fall straight down. And if the man jumps straight up and down, he will still see the rain fall straight down. But if the man walks perpendicular to the falling rain, he will have to tilt his umbrella in the direction of his motion, in order to stay dry. This is caused by the same Galilean effect as dropping a cannonball from the mast. If the raindrop is 10 feet away when it is at eye level, and is at 0 feet away when it is at foot level, then it appears that the raindrop has moved towards you at a slope. You don't have to worry so much about the rain that is currently above your head, as it will be behind you before it can hit you. This also means that it is the velocity of the observer that causes this apparent position of the star, not the observer's position, which would have been parallax. In September, the Earth is moving at its most perpendicular to the parallel light rays of Gamma Draconis to the north, and the telescope needs to be tilted a tiny amount towards the north. To get an idea of the small amount of tilt, here is a 20 arcsecond difference, and here is a degree difference. In December, Bradley's zenith is moving towards the star and is parallel with the light rays, and therefore the telescope can see the star at 0 arcseconds from zenith. In March, the Earth is moving perpendicular, in the opposite direction it was from September, and the telescope needs to be tilted in the opposite direction from the September measurements. In June, the Earth is moving away, in parallel with the light rays, and the telescope can again see the star at 0 arcseconds. Bradley explained the results of his experiments with the corpuscular theory of light, as the light was acting similar to raindrops falling. Using this idea, Bradley, in 1728, was able to make speed of light measurements, which were relatively close to the ones we know today. But more than that, Bradley discovered that the speed of light was a constant, as light from every star arrived at the same velocity. It may not seem like it today, but this discovery had profound implications. The idea that the speed of light didn't appear to change meant that the ether is stationary in the Earth's frame of reference, which is strange, as the Earth is always changing directions as it orbits the Sun. The effects of aberration will not be explained for another 200 years, and all those years are spent trying to explain how to fit stellar aberration into the other theories. Newtonian mechanics of planetary motion, however, was starting to demonstrate that Newtonian mechanics was not a totally accurate understanding of the universe. Just as today we know that Einstein's general theory of relativity must not be the whole picture, as it does not fit perfectly with quantum mechanics. And so too did the physicists of the 18th century come to realize that Newton's mechanics were great for small and close everyday equations, but they could not accurately explain planetary motion in what is famously called the three-body problem. Systems like the Sun, Earth, and Moon were not calculatable with Newton's mechanics, and attempts to use them provided the wrong answers. One of the scientists working on this problem was the prolific mathematician Leonhard Euler, who, in the years between 1744 and 1746, became an anti-Newtonian theorist because of his work trying to use Newtonian mechanics. Euler eventually returned to the Cartesian vortex theory of the ether. However, the vortex theory predicted the motions of the planets would speed up, whereas the stationary ether theory predicted, as Newton suggested, that they would slow down the motions of the planet, and Euler had found that the Earth appeared to have lost a day since Ptolemy's observations of the changing length of a year. Euler also flipped Newton's ether idea, stating that the ether may be denser in space and rarer near the Earth and other bodies, making gravity an effect where we are pushed into the Earth as opposed to pulled or attracted into the planet. Euler never found a solution to what the ether was. However, his research into waves helped support his belief that gravity and other phenomena are caused by an impulse, as suggested by Hooke. Euler also took on Newton's optics, researching light and color, discovering that things like diffraction were better explained by light as a wave. This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you.